So don't leave today without giving me homework 2.1, but let's start. Okay, so sequences and sets, that's 2.2. And then this is everything in the section that we're going to cover, so it's a relatively small section. So, starting with the definition, we briefly went over this last week. Let's make sure it still makes sense. So, some sequence an is bounded if and only if there exists some real number r such that every term in the sequence, when you take its absolute value, is less than or equal to m. Remember, another way that we could write this absolute value right here is like this. Negative m less than or equal to an less than or equal to m. So if I can find some m such that m and its negative value sandwich this, then it's bounded. Make sense? Anything strange about that? I wonder if I'm supposed to have... No? That's right. Okay. So if we're good with that, then let's do the next proof. We're going to prove that if the sequence converges, then it's bounded. Make sense? Alright, so let's do the proof. Proof. We're just proving this, so I won't bother writing it out. 1. So let's start by giving up our sequence. Let an such that the limit of an is equal to a. So start by grabbing some sequence that we know converges to some number, call it a. Good so far? 2. Now remember what I'm trying to do. I'm trying to find some m such that absolute value of an is less than or equal to m for all n greater than or period, for all n in n. So I'm trying to find the n that makes this true, and then I'm done. Now, since I know that the sequence converges, then I know I can pick any epsilon I want, and for any epsilon I pick, let me write it out, then I know that an minus a is less than, pick any epsilon I want, I'll just pick 1 to keep our numbers simple. An minus a is less than 1 from some index onwards. For all n, I should say that there exists an n that makes this true, sorry. Then there exists some some index in the sequence such that from that point onwards, this absolute value is less than or equal to 1. Since an converges to a, right? Here's a big idea of the way that we're going to think about this. I know that the sequence is less than 1 from some point onwards, and then there's only finitely many terms that come before big N, right? So from big N onwards, I'm guaranteed that my sequence is within some distance of A. Looking prior to that, I'm guaranteed that those terms are within whatever the biggest term is. Make sense? So if my sequence looks like if we were to plot it, if it looks something like this, and then it's converging, so I know from here onwards we're always within 1 of A, then I know if I just look at the max of all these other points, then my whole sequence is going to be within whatever the max was of all my points prior to that. Make sense? So that's big picture where we're going to be going with this. So maybe it will help to just do it rather than trying to get picture first, and then maybe come back to picture. So then I know that from some index onwards, this is always true. Well, that being true, let's see, what does that give me? So from this index onwards, then let's see. So rewriting this, how can I rewrite this? That's negative 1 is less than an minus a. Remember, I'm trying to get an less than or equal to something. So is less than 1. How do I want to do this? or maybe we'll do it this way. I know that this is less than 1, therefore the absolute value of an, which is equal to the absolute value of an minus a plus a, is less than or equal to, use triangle inequality, I'm going to group these two together and this one by itself. Okay, and then from up here, I say that this is less than 1. So this whole thing is less than 1 plus the absolute value of a for all n greater than or equal to our index. You see what I've done so far? So from some index onwards, I've shown that this sequence is bounded. An is less than 1 plus the absolute value of a, whatever that is, from some index onwards. Am I losing you? No? Okay. So we've shown it's bounded from some index onwards. Now we just need to handle the first n terms in the sequence.
How did you get 1?
Oh! Absolute value of a minus a is less than 1 from this index onwards.
Right.
So I'm trying to get an less than something, so rather than trying to be clever with this, I just decided, let's just start with an, and then make this pop up. So that was my, at first I didn't deal with this, and I decided to backtrack and do it this way, and that worked out pretty nicely. So now, we need to find our m for let m equal the max of the first term in the sequence, the second term in the sequence, or the absolute value of them, because we need m to be positive, whatever it is, right? Since m has to be greater than or equal to an absolute value, we always need the positive terms. Of course, the max is always going to be positive. Oh, we always need to be greater than or equal to the absolute value of an, so always make sure it's the absolute value of the term. There we go, that's right. So absolute value of a2 dot absolute value of a sub n minus 1, and then 1 plus absolute value of a. Okay. So m is either going to be one of these terms. So we have one of two cases. Either 1 plus the absolute value of a is greater than the absolute value of every term in the sequence, or there was a term in the sequence before big N bigger than this when you take its absolute value.
Wouldn't you have a sub the absolute value a sub n in there, because 1 plus the absolute value of a is greater than the absolute value a sub n?
I know that 1 plus the absolute value of a is greater than the absolute value of a sub n.
So you don't need it in that set, right?
So I don't need it here because this is true for all n greater than or equal to big N. So I just need to get all the previous terms in the sequence. So we've got our sequence. A1, A2, A3, A sub n minus 1, A sub n, A sub n plus 1, and it goes on forever, right? So I know that from this point in the sequence onwards, this way, the absolute value of all these terms is less than 1 plus the absolute value of a. 1 plus the absolute value of a, that's just a number. So I'm guaranteed from this term onwards, our absolute value is always less than this.
What does a represent? Oh, that's the limit. Okay.
Oh yeah, a is the limit of the sequence. Remember, this sequence converges. It's closer and closer to something.
Okay.
That's high level what we're doing.
So
If an converges, then it's bounded.
from an onwards, like upwards, then it's always going to be less than?
Yeah, from an, every term in the sequence from here on out is going to be less than 1 plus, when you take its absolute value, it's going to be less than 1 plus the absolute value of a.
Are you sure? Because it seems like anything less than an would still be less than. Like, how can you take something bigger than an and say that it's still less than that?
A and n, just because you increase the n doesn't make a sub n bigger. It's just the next term in the sequence. So remember, this sequence could be something along the lines of, alright, let's make an arbitrary sequence. 3 over n. Right? So what is this equal to? What's the first term in the sequence? 3. What's the next term in the sequence? 3 halves, thank you. 3 halves. Next. 1. Next. 3/4. Next. 3/5. Dot, 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 and it goes on. So here's what I did up here. I said if you have a sequence that converges, then there comes a point in the sequence, and this sequence is starting right here. There's an index in the sequence, in our case, that starts right here, such that from that point onwards, you are within 1 of what it converges to. In this case, what does it converge to? 0. So in this case, our A is 0. So I'm saying from this index onwards, the absolute value of these terms is less than 1 plus 0 in this case. So this is less than 1 plus 0, this is less than 1 plus 0, this is.
Okay.
Now I want something that bounds the whole sequence. I'm showing that the whole sequence is bounded. So I'm saying, look, either this whole sequence, since from this point onwards I know that I'm less than 1, then my whole sequence is either going to be less than 1, or less than this, or this, or this. I know that all these are less than 1, now I just need to look at these ones. And if they're bigger than 1, I'll just pick that as my new max. So I look at this one, oh, that's still 1, so we're still good. Oh, that's bigger, so now our max is 3 halves. Oh, that's bigger, so now our max is 3. So n is equal to the absolute value of a1 in this case, 3.
Okay.
Make sense? Okay, so I know since it converges, then from a sub big N onwards, we're less than or equal to 1 plus the absolute value of a. And then I just look at all the previous terms and let n be the max of whatever, n be the max of these. If one of the previous terms is bigger, make that the max. Otherwise, use these terms. We understand what n is now? Okay, so then we're done. And therefore, a sub n is bounded. Right?
Okay.
We found some number that's greater than or equal to the absolute value of an for all n, for every index.
So I have a question. Is the reason we couldn't just take the max of the sequence because the sequence isn't finite, but doing what you did before by finding 1 plus?
Wonderful. So we know that every finite sequence has a max element. We cannot say an infinite sequence has a max element. That's something you have to prove whether or not it does or doesn't. Because some do, some don't. Right? Because if we look at the interval 0, 1, not including 0, not including 1, there's no max element in there.
Right.
So yeah, I'm only guaranteed to have a max if there's a finite number of terms. I shouldn't say it that way. I am guaranteed to have a max if there's a finite number of terms. That's how I should say it. So, good eye. Anything else? Okay, so we just proved if it converges, then it's bounded. Our next definition. Okay, this was, oh no, this one, nothing weird with this one. So what does it mean for a set to contain a sequence? Easy. If every member of the sequence is in the set, then the set contains the sequence. Right?
The sequence is a subset of it, right?
If, remember that sequence is in the set, if the range of a sequence is a subset, is one way that you could say it, yeah. Because remember, a sequence is really a special type of function.
Right.
Maps natural numbers or something. Okay. So is there anything weird about this, or do we need to see some examples? Or do you think you got it? A set S contains some sequence A n, if and only if A sub n is in S for every term. A1 is in S, A2 is in S, A3 is in S, they're all in S, then S contains a sequence. Pretty straightforward. Okay, so here's the weird one. The one that seemed weird. S, so some set, S is a set. Some set S is dense in R. Remember what it meant to be dense in R? It means for any teeny tiny open interval A, B I pick, no matter how close together I make A and B, I'm always guaranteed to have some element of S in there. That's what it means for S to be dense in R. I can't make an interval so small that I don't get one of those numbers. Right? So, some set S is dense in R if and only if for every real number there exists a sequence AN in S such that the limit of that sequence is that real number. So let's give an example really quick. I know that, give me a set that's dense in R.
The rationals.
The rationals are dense in R, right? Rationals are all the fractions you can make. We proved 2 weeks ago that the rationals are dense in R. So what is this saying? That's saying then pick any real number you want, like the square root of 2, which is irrational. Pick any real number you want. I should be able to find a sequence of rationals that converge to that number. That's what that's saying. S is dense in R if and only if for any real number you pick, I can find a sequence in my set that converges to that real number. So that's what we're going to prove. If it's dense, then for any real number you pick, I can find a sequence that converges to it, and vice versa. If we have some set such that I can always find a sequence in it that converges to any real number, then that set is dense in R. So, both ways. Alright, so we'll do the proof. You can see what we're doing, so I'm not going to bother writing it out. And we'll start by going from S is, we'll go this way first. So what do I need first? Let S be dense in R. And let X be any real number. I need to prove that I can find a sequence in S that converges to X. That's what we're showing. I'm showing that if S is dense in R, then for any real number you pick, I can find a sequence in S that converges to that real number. Make sense where we're trying to go? Yeah? Okay, 2. Let AN be a sequence such that, how do I want to say this? That the nth term is in, be a sequence in S. Maybe we'll make an observation first and then we'll construct a sequence. So, observe that since S is dense, it has a member AN in X to X plus 1 over N. So since S is dense, then for any open interval I pick, S has to have a member in there.
Why did you choose that one?
So when N is 1, then from X to X plus 1, I know that S has to have a member called A sub 1 in there. When N is 2, I know that S has to have a member called A sub 2 in there, etc. So this is an open interval that keeps getting smaller and smaller and smaller and smaller, so it's getting closer and closer and closer to X. So I'm going to create a sequence that gets arbitrarily close to X. But these, so let's see. Let AN in S, let AN be the sequence in S such that a sub n is in x plus 1 over n. You see how it's valid for me to pick that sequence? So here, let's write it out real quick. So first off, let's look at x to x plus 1. Does S have a member in there? Yeah. So grab that member, whatever it is, and we're going to call that A1. Whatever it is. We know that there's something in there. So whatever element S has in there, call it A1. Okay. Now what about x to x plus 1 half? That's an open interval. S is dense in R. Therefore, S has some member in there. Maybe it's the same thing as A1. Maybe it's something different. We don't care. Whatever the member is in there, call it A2. Similarly, it has a member in here. Whatever that member is, call it A3. Dot, dot, dot. Similarly, it has a member in, put anything down here you want. And we'll call that A sub 1, 0, 0, 0, 0, 0. So you see how this interval is getting closer and closer and closer to x? Right? We're taking x and we're adding a teeny tiny number to it. Hardly changing it. And we're still guaranteed that there's some term in S in between there, call it that. And so in general, when this is n, we're going to call the term in there A sub n. Make sense for our sequences? Make sense that it's valid that we can do that? Okay. So, let A and B the sequence in S such that the nth term is in that thing. What do I need to show? I need to show that the limit of an is x. So I need to show that for any epsilon you pick, I can find, well, we can probably just use the comparison line on this one. So if an is within this for every natural number n, then another way that we can write this is that x is less than an is less than x plus 1 over n. You see how that's just rewriting it?
So you're saying it's pretty similar to absolute value.
Well, that's just what needs to be in this interval. If an is in the interval x to x plus 1 over n, that means an is between those.
Yeah.
So that gives us, if an is greater than x, an is definitely greater than x minus a positive number. So I'm going to say x minus 1 over n is less than a sub n is less than x plus 1 over n, right? Because we only made this number smaller. So if an was bigger than x, an is definitely bigger than x minus 1 over n. Now I'm going to plus or subtract x from all three sides of the inequality, if you'll let me say it that way. So that gives me this minus x leaves us with negative 1 over n is less than an minus x is less than 1 over n. Good? What does that give us?
Gives you that the absolute value of an minus x is less than 1 over n.
The absolute value of ax minus x is less than 1 over n for all n greater than or equal to what? Just all of them.
Yeah.
For every natural number. So for all n greater than or equal to, we'll just pick one. 1 in this case, doesn't matter. Now, by the comparison lemma, remember what the comparison lemma says. If you can find an minus something such that it's less than something that you know converges times a constant for all n starting at some index, then this converges to this. Do you remember the comparison lemma, or do you want us to just finish proving this directly?
I kind of remember the comparison lemma. Like, I think I could write it out, but I'm not sure I understand it.
Comparison lemma. Comparison lemma says, so if I have bn minus b is less than or equal to c times an minus a for all n starting at some index. If this is true, then that means that the limit of bn is equal to b, where an converges to a. So if I can get this is less than or equal to a constant times the absolute value of an minus a, so maybe rewrite this one more way to help see how we're using the comparison lemma directly. That gives me that the absolute value of an minus x is less than or equal to 1 times the absolute value of 1 over n minus 0 for all n greater than or equal to 1. Maybe just add some stuff in there that we don't really need just to see exactly how we're using the comparison lemma. So the comparison lemma says if an converges to a, and this inequality is true from some index onwards, then bn converges to b. So I have this converges to this, we've already proved that, 1 over n converges to 0. And we have that this inequality is true from some index onwards, therefore this converges to this. Good? We could have also proved it converges directly real easy. I could have said let epsilon be a positive real number, then there exists some index n such that 1 over that index is less than epsilon, and then this would be less than epsilon from some index onwards. It would be real easy to do either way. But we'll just say it with the comparison limit. Therefore, the limit of an is equal to x by the comparison limit.
Wouldn't that be just less than, not less than or equal to, on the line right above?
Well, if it's less than, then it is less than or equal to, and the comparison limit uses less than or equal to. So I just adding stuff that we didn't necessarily need to, just to make it as clear as possible that the comparison lemma holds. Anyways, okay, so we've shown it this way, right? We've shown that if S is dense in R, then for any real number x you pick, I can find a sequence in S such that the limit of that sequence is x. Now I need to point it the other. Now I need to do it the other way. I need to say if I've got some set, and all I know about that set is that for any real number you pick, I can pick a sequence in that set such that the limit of the sequence is the real number you picked, then my magical set happens to be dense. So now let's do it this way. So let S be a set such that for all x in R, there exists a sequence an in S such that the limit of the sequence is equal to x.
Sorry, are you missing out?
Nope. Okay. So, this is our given. What do we need to do? We need to show that for any interval you pick, we can still, will you be confused if I use A, B?
Really good question. Wouldn't it really just be the image of an rather than the entire sequence, technically, since the sequence isn't a set?
We defined what it means for a sequence to be in S. A sequence is in S if the image is a subset of S, is one way you can think about it.
Okay, I just think it was different.
Okay. So now we need to show that S is dense. How are we going to show that S is dense? We need to show that for any interval we pick, we're guaranteed to have an element of S in there. Right? So let A comma B be an open interval. Specify that so we don't think we're talking about an ordered pair. So now I need to find some element in S greater than A and less than B. And if I can do that, S is dense, right? Well, I know that for any real number I pick, I can find a sequence that converges to that real number. What seems like the most useful real number we could pick here?
1.
A plus B divided by 2.
A plus B over 2. Pick the number in the middle of those two things. If I pick the number in the middle of those two things, and I know that I have a sequence in AN that converges to that number, then I can show that there is a term in AN in there, right? So 8. So then there exists some sequence AN in S such that the limit of AN is equal to A plus B over 2. Jeez. Okay, so if I know that my sequence converges to A plus B over 2, then what does that give me? Then for any epsilon I pick, I know that my term will be within epsilon of this. What's the epsilon I'm going to want? Let's draw a picture real quick over here. So I've got A here, I've got B here, A plus B over 2 is right in the middle. What's the epsilon I'm going to want to choose to make sure that I pick a term inside of here?
Just either A or B.
No, because remember, A could be a big number. This could be 10,000, this could be 10,001. If I get my terms within 10,000 of this, they could still be clear out here. You see what I'm saying?
Right, yeah.
What's the distance I want?
So A plus B over 2 minus A?
Exactly, half this distance is what I want. So B minus A over 2 is the easiest way to say it, but you said the exact same thing, just harder way.
Why?
So I know, since my sequence converges to this number, then I know it gets, that terms in my sequence get within whatever distance I choose of this number. I want to pick a distance that makes sure that they're within AB. So pick this distance.
Why?
Because if I find a term, A sub n, that is within this distance of this number, that forces it to be in this interval. It has to be somewhere over here, somewhere over here.
Right.
Either way, it's in AB. Remember, we're just trying to find something in the open interval AB, and we're done. We're trying to show that our set is dense.
Oh, right.
We're trying to show that for any open interval AB you pick, I can find a point in my set that's in there. Good? So, pick any epsilon I want. I'm going to pick B minus A over 2, half the distance, that's this distance right here. Half the distance between these 2 points is how I'm coming up with that. B minus A is this distance, take half that. So, 9. Then, the absolute value of AN minus A plus B over 2 is less than B minus A over 2 for all n, then there exists n, sorry. There exists some index n such that the absolute value of the terms in my sequence minus what they converge to is less than any epsilon I pick from that index onwards. Right? AN minus this number has to be less than this distance from this index onwards. Which means A sub big N, wherever it is, A sub big N has to be somewhere in here. A sub big N plus 1 has to be somewhere in here. A sub big N plus 2, plus 3, plus 4, whatever from this point onwards, because they're getting closer and closer to this point. This is where they converge to. Good? Am I over-explaining? Okay, so if this is true, from this index onwards, we're just going to rewrite this inequality. Then, negative this is less than this is less than positive this. Then, negative b minus a over 2 is less than a sub n minus a plus b over 2 is less than b minus a over 2. You good with that?
Mm-hmm.
So this gives us, I'm just going to add a halves and b halves to both sides. So, notice we have negative b halves and positive a halves. Here we have negative a halves and positive b halves. Sorry, we're going to add it. Let me rewrite this really quick. So this is negative b halves plus a halves. This is b halves minus a halves. And I'm going to add a halves and b halves to both sides. When I add b halves here, that cancels that out. Add a halves leaves me a. When I add b halves over here, that gives me b. When I add a halves, that cancels out with this. Because I'm adding a halves and b halves to both sides. And adding a halves and b halves to this just leaves me with a n. You follow that? The algebra there? So adding this term to all three sides, adding it here gets rid of that, adding it here leaves me with an a, adding it here leaves me with a b.
And we know that a n is in sequence. Now it's the one, right?
So I know that this is true for all n greater than or equal to big N. 11. Therefore, a sub big N is in a comma b.
A sub big N?
Yeah. If this is true from big N onwards, it's true for big N. It's also true for big N plus 1. It's also true for big N plus 5,286. We found infinitely many terms in there. We just need to find one.
Why didn't you use little one?
Little n is a particular term.
Oh, okay.
It's like when we're talking about a function, I'll use f of x equals x squared to mean we're not talking about a particular term, but I'll use f of x sub 1 is equal to x1 squared when I'm talking about a particular number, x1.
Right.
Similar thing. We use big N to talk about a particular index, little n to talk about an arbitrary index.
Hard to keep track of sometimes.
Yeah, you gotta get used to it. That's why kids have a hard time the first time you introduce them to variables with subscripts. Because now we're talking about a particular variable,
Yeah.
right after you hammer variables home on them. So.
Doing that in street math was rough for a while.
Yep, just gotta get used to it. Anyways, therefore what?
Therefore, S is dense.
S is dense in R. Wonderful. And there's our proof. Any questions on the proof? Nice, useful little theorem. So now if you know a set is dense, you instantly have this other information about it. And if you have this other information about it, which seems like more arbitrary when would you ever have that, turns out you actually will more often than you think, then the set is dense.
When will that happen?
I instantly start thinking of topology when I see it. I can't, so I don't have something on the top of my head, but I imagine that we'll probably use it here. We'll see. Anyways, but any questions about the proof? All right. Is that camera going? Okay. I don't remember pushing the button. Or So now, where are we? This one. This one's just a corollary of this. I don't even know if we need to write anything because we'd just be writing one line basically saying it's true. So what does this say? This says for any real number you pick, there exists a sequence of rational numbers such that the limit of that sequence is that real number. What would we say? We'd say, observe that Q is dense in R, therefore by this proof, it's true. So I guess he just really wanted to hammer home the idea that now, for any real number you pick, you can always find a sequence of rational numbers that converges to that real number. So that's something you can arbitrarily use now. For any real number, you can always say, well, I know there's a sequence of rationals that converges to it, and maybe some reason that's useful to you. Okay, so are you all okay with this one? Okay, then we'll move on to this one. What does that say? If every term in our sequence is greater than or equal to 0, then and the sequence converges, then whatever it converges to is greater than or equal to 0. That one seems kind of obvious, right? So let's prove it.
A being any term in the sequence of A, right?
Every term in the sequence.
Right.
Every single one.
So let's see. Let AN be a sequence such that AN is greater than or equal to 0 for, well, we'll just say it, is greater than or equal to 0 for all n in N, comma, and assume the limit of AN is equal to A. So now it remains to show that A is greater than or equal to 0. Right? Good? Okay. So let's see. How do we want to do that? So I know since AN converges to A, then I can always find an index such that not sure how I'm going to do this yet, so I'm just going to start playing. Then there exists some index n such that AN minus A is less than epsilon. I can pick something there. I don't know what I want to pick yet. For all n greater than or equal to n. What would I want to pick? Let's do some scratch work to the side, see if we can figure out what it should be, and then come back. So then I know negative epsilon is less than AN minus A is less than epsilon. That would give me that A minus epsilon is less than AN is less than A plus epsilon. No. So I can get this AN minus, how would I get epsilon to be the half the distance between those? Let's look at my notes, see what I did. Where did that one? Where did that? Oh, I did this one by way of contradiction. That seems easier. So, assume by way of contradiction that A is a negative number. Alright, and then let's see what that leads to. Right here. Okay. Assume by way of contradiction that A is less than 0. Then that would be less than A halves, so it's just N such that that is less than A halves. Well, we'll just see where it goes. So then, since I know that an converges to n, then there exists some index, big N, in the natural numbers such that an minus a is less than, pick any term I want. I'm going to pick negative a halves. Why negative a halves?
Because a is a negative number, so.
Yeah, because a is a negative number, so here's what I'm doing. Here's 0. We're assuming a converges to a, some negative number. So I'm going to find a term that is within a halves of a. So I'm going to find some term that is within here and say, look, that term's less than 0. So that contradicts every term being greater than or equal to 0. So that's big picture how we're going with this. And yeah, since a is negative, I can only do less than a positive number, so I pick negative a halves. Or the absolute value of a halves. Same thing. Right? Positive number? You good with this as a positive number?
Yes.
Okay. So, since a converges to a, then for any positive number I pick, namely negative a halves, there exists some index in the sequence such that this is true for all n greater than or equal to n. Okay. Let's see how we want this. Then, rewriting this, we have a halves is less than an minus a is less than negative a halves. Right? Write the negative of that over here. Remember, a is a negative number. So negative less than positive. And then, adding a to all three sides gives us 3a halves is less than an is less than. Over here we have a halves. But we know that a halves is less than, well, we'll just write it this way. Then an is less than a halves. And what do we know a halves is less than?
0.
0, which gives us an is less than 0 for all n greater than or equal to n. So, maybe we'll just pick one. Then a sub n is less than 0, contradiction. We found some term in the sequence that doesn't satisfy this. This is true for all n in n. We found one where it's not true, contradiction. Therefore, a is greater than or equal to 0. Yeah, that was easier to do by contradiction. Good? Remember what we were proving. We were proving that if an is a sequence such that all its terms are greater than or equal to 0, then whatever it converges to is also greater than or equal to 0. So an is a sequence that converges. If all of the terms in a sequence are greater than or equal to 0, then what converges to has to be greater than or equal to 0. We said assume by way of contradiction that what it converges to is not greater than or equal to 0, which is the same thing as less than 0. We're going to show this leads to a contradiction. What contradiction is it going to lead to? It's going to lead to me finding a term in the sequence less than 0. The sequence has to have every term in the sequence greater than or equal to 0. I'm going to find a term in the sequence that's less than 0 if you allow this to happen. Contradiction. How do I do that?
Hang on. How does that contradict it? You're assuming that a is less than 0.
So,
Therefore, any term in the sequence would be less than 0.
I know that an is a sequence such that an is always greater than or equal to 0. A sub 1, it has to be somewhere over here. A sub 2, it might be 0, but it can't be over here. A sub 3, over here. A sub 4, over here. Whatever. All the terms in the sequence have to be greater than or equal to 0. And they converge to some number. I don't know what they converge to, but they converge to some number a.
Except we're not saying that.
Huh?
We're saying that a is less than 0.
Right, so we're going to assume by way of contradiction, we're going to make an impossible picture. I'm going to say all the terms in the sequence are over here, but somehow what they converge to is over here, and so this leads to something impossible.
Okay, that makes more sense. Okay.
And what's the contradiction? We're going to find an a sub big N, some term in the sequence, that's now negative. which is a contradiction. All of an impossible picture. Remember, we're creating an impossible picture. All the terms in the sequence are over here. We know that.
Oh, okay. Right.
I'm going to show that if A is over here, that leads to a term in the sequence being over here. Contradiction.
Which is
They
false.
can't all be over here and have one over here.
Okay.
How do I find one over here? I pick the distance. I pick half this distance. So this distance right here is negative A.
Right.
So half the distance is negative A over 2. So I pick the distance negative A over 2, which means that if you are within negative A over 2 of A, then you're in this interval. If you're in this interval, you're for sure negative.
Mm-hmm.
So I said, since A converges to A, then it gets within any distance I want of A. From some index onwards, my sequence has to be within this distance of A. That's what means to converge. So, that's what I'm saying here. There has to be some index n such that the terms of my sequence are within negative A halves of what they converge to from that index onwards.
Okay.
But if they're within this distance of A, then that leads to this being true, 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 all the way to we get an less than 0 for all n starting at that index. So that means at that index is less than 0. Okay, here's my term I found, less than 0, contradiction.
Interesting. Okay.
Feel like you got it? Okay. That was that. Okay, now we're going to do proof. I don't know why I did a CN. Probably because I didn't want to use A since we use A in the interval. So if Cn is a sequence in the closed interval AB, and the limit of Cn, so if Cn converges and it's in this interval, then the thing it converges to is also in the interval. So if I look at the closed interval,
Oh yeah.
going from some point A to some point B, if I look at the closed interval, then any sequence in this interval, whatever it converges to, has to also be in the interval. C, whatever my sequence Cn converges to, C, also has to be in that interval. Now notice, it might appeal to your intuition that this is true for closed intervals, but notice it's not true for open intervals. Right?
Does it converge to A or B?
Look at this interval. 0, yeah, 1 over n. Sorry. 0 to 1, and look at the sequence in there, 1 over n. Notice every term in this sequence is in here, right? Oh, let's go to 2. Thanks. Okay, now every term in this sequence is in the interval 0 to 2, right? This is 1, 1/2, 1/3, 1/4, 1/5, 1/6, 1/7, 1/8, 1/9, 1/10.
Right.
Getting smaller and smaller and smaller.
Oh, but never actually touching either of those. Okay.
But this is never 0. You can't pick an n to get 0. It will always be slightly bigger than 0. This is always positive. So, 0 is always less than 1 over n is always less than 2 is another way I could say it.
Mm-hmm.
So, this sequence is in this set, but it converges to something that's not in the set, namely 0. So it's not trivial that just because a set contains a sequence, that the set also contains the limit of the sequence. We're saying in the special case where it's closed,
Closed means that 0 and 2 can both be in there, right?
yeah, so closed changes it from less than to less than or equal.
Okay.
So this is all the x between 0 and 2 inclusive.
Right.
So in this special case, when you have a set like this, a closed set, then the limit of the sequence is also in the set. That's what we're proving. Make sense what we're trying to prove?
Yes.
Alright, one response is enough for me. Okay, so let's do our proof. I'm not going to bother writing it out, but you know that we're doing this one, right? So what's my first line going to be?
Let Cn be in AB.
Yeah, so let AB be a closed interval, and let Cn be a sequence in AB such that Cn converges to C. So, oops, capital L. Let AB be a closed interval and let Cn be a sequence in AB such that the limit of Cn is equal to C, such that it converges to something, call it C. It needs to show that C is in the closed interval AB. And if we can show that C is in AB, then we're done, right? Alright, let's see how I say this. Oh, I'm going to use my previous proof. So I'm going to create a sequence such that every term in the sequence is greater than or equal to 0. Therefore, what it converges to is greater than or equal to 0. Okay, so
Is that the best way to do it?
I don't know. It's just what I have written here. If you come up with another way, let me know. So I say, observe that Cn is less than or equal to B for all n. Well, we'll put the for all when we're done. Cn is always less than or equal to B, right? Because it's in the sequence. Which gives me that B minus Cn is less than or equal, other way. Subtract Cn from both sides of the inequality. 0 is less than or equal to B minus Cn, and this is true for all n for every natural number. With me so far?
Yeah.
So we just created a new sequence where every term in the sequence is greater than or equal to 0.
Okay.
Make sense? Okay. So then the limit of B minus Cn, whatever it is equal to, we're going to actually evaluate it, but we also know it has to be greater than or equal to 0 by the previous proof. So what's the limit of this?
It's just B minus C.
It's just B minus C, right?
How? How did you do
All right.
that?
We'll take it one step at a time. This is equal to the limit
Oh,
of
right, okay.
B plus, we could say, I could view that as -1 times the sequence, I guess. And then do plus, but I think you're okay with this, right? And then that is the same thing as the limit of a constant is a constant, and then we already know that the limit of Cn is C. So we know that the limit of that is equal to this, and we know that B minus C, this limit, has to be greater than or equal to 0 by the previous proof. Right? Remember what this proof said? This proof said if every term in my sequence is greater than or equal to 0, then whatever it converges to is greater than or equal to 0. I know that B minus Cn is greater than or equal to 0. Therefore, the limit of that has to be greater than or equal to 0. So, let's see. I think I'm going to have to do that again with the A, and then somehow sandwich C between A and B, because I need to get C between A and B. So,
So let A be greater than or equal to Cn, and then just do the same thing from there?
well, we're going to do a similar thing, but we have to switch to Cn and to B. So now I'm going to repeat this step, and I'm going to end up with c minus a is greater than or equal to 0. I think you'll get it as I go. Observe that a is less than or equal to cn. Notice the parallel on line 2. I'm basically redoing line 2, but slightly different. A is less than or equal to cn, right? If cn's in this interval, it's always greater than or equal to a. So cn's greater than or equal to a. What does that give me? That gives me, subtracting a from both sides, that gives me 0 is less than or equal to cn minus a for all n in n. Now I'm going to redo line 3 almost identically. Then the limit of cn minus a is just equal to c minus a, and c minus a is greater than or equal to 0. Also by that proof. Did you follow all of Form 5?
Yes.
Okay, so now we're just going to combine this. I know that c minus a is greater than or equal to 0, and I know that b minus c is greater than or equal to 0.
You could, well, actually.
Oh, so that just gives me both my inequalities. So then I get, then from here I get, then b is greater than or equal to c, and from here I get c is greater than or equal to a, which gives me b greater than or equal to c greater than or equal to a, which gives me c is in the closed interval ab. You follow that? This inequality, add c to both sides, gives me b is greater than or equal to c. This inequality, adding a to both sides, gives me c is greater than or equal to a. So that's how I got that and that, and then just combine it. B is greater than or equal to c, and c is greater than or equal to a. C is between a and b, or in other words, c is in there. Good? Nothing weird?
Super easy peasy.
Definition, a set S is closed, provided that for all a, n, and s, where a is the limit of a, n, then a is in s. Okay, so basically what we just did here is what we mean by a closed set. We just barely proved that every closed interval is a closed set. What's a closed set? It's a set such that every sequence in the set that converges, it converges to a number in the set. So take some set of numbers. If every sequence I can find in there that converges to a number that's also in the set is closed.
That's the second definition for, no, never mind.
Before we talked about closed interval.
Yeah.
Now we talk about a closed set. This isn't how we'll define it in topology. We'll have a different definition for a closed set in topology, and then we'll prove that a closed set has this property in topology. But topology, we're very interested in what we call open and closed sets. This is a closed set with the standard topology on the real numbers. Whereas in topology, we'll just talk about closed sets in general.
Will you say that one more time?
Yes. So if I have a set like 1 to 3, so here's some set of numbers. If you have a set such that any sequence in the set that converges, so come up with any sequence I want that's in this set that also converges. If what it converges to is also always in the set, then the set is closed.
Oh, okay.
So essentially what we did up here then, if we use this definition, what we proved up here is that every closed interval is a closed set.
Okay. Kind of was the opposite of that.
Not the opposite. We could have, using
Not
this
the exact
terminology, we could have said, prove this interval is a closed set. And that means exactly what we have here. Prove that every sequence in this set that converges to a point in the set. proved that this set is closed. Same thing. Make sense? Okay, now it makes sense to me why he ended with a definition.
Is that the end of section 2?
He had 2 examples. So, example. The rationals are not closed. How can we show that the rationals are not closed? What does it mean to be closed? It means every sequence in there converges to a point in there. But we know by this that for any real number I pick, I can find a sequence of rationals that converge to that number. So I know that there exists an in Q such that the limit of an is equal to the square root of 2 is not in the rationals. That's how I know the rationals are not closed. I can find a sequence in the rationals that converges to a number that's not in the rationals. That's what we proved up here. We proved that for any real number you pick, I can always find a sequence of rationals that converges to that number. Square root of 2 is a number, therefore there's a sequence of rationals that converge to it. How do I know that? Because Q is dense in R. Ta-da! Another example. We kind of already did this one, slightly different. The sorry. 0, 1. This interval is not closed. And how do we know? The sequence 1 over n. This sequence is in there. Every term in this sequence is greater than 0 and less than or equal to 1. Therefore, every term in the sequence is in there. However, what does this converge to? 0. 0 is not in there. Therefore, this set is not closed. It's only closed if every sequence that's in here that converges to a point in here. Make sense?
Okay, so take the example, open bracket, negative infinity, comma 1, close bracket.
Negative infinity, comma 1, close bracket.
Mm-hmm.
Oh yeah, okay, that's a great one. Is that open or closed?
That's closed, right?
It's closed. Good.
Right?
Mm-hmm.
Yeah, we know that. How can we rewrite this? We can rewrite this as negative infinity to 0 unioned with 0 to 1. We know that this is closed by the proof up there, and we know that this is closed because any sequence with all negative terms converges to a negative number. Or with non-positive terms converges to a non-positive number. Right? So, yeah, good. Another example, what about R? Is that closed?
Mm-hmm.
What about the empty set? Is that closed?
Yeah.
Yes.
It's open.
Every sequence in there that converges to a number in there. There isn't any sequence in there, so there isn't any sequence in there that converges. So, vacuously true, right? Okay, I think you got a good feel for that. So, we'll take a break there. I'll get ready for the next section. But yeah, that's the end of 2.2. We'll move on to 2.3. We just might cover what we're supposed to cover today. Wouldn't that be great? Yeah, you can go on break. You don't have to sit here and watch me write if you don't want. But if that's your thing, that's your thing. Alright.
I just need to take a break at 10:30. Talk to the teacher.
At 10:30?
Yeah.
Maybe I'll just turn off the recording and do it in 2